Well, hello and welcome everybody. We made it through the first week, just 4 more to go. Before we get started, does anybody have any questions they'd like me to answer or any concerns? Nope, everybody's doing all right. Let me share my screen. So today is Monday, and the announcements are, for today at least, well, the nice thing is there's nothing due today, but you should, it'd be in your best interest to start a WebAssign on 2.3, which is what we're going to cover today. And you could start, there's one problem on the summary sheet. A reminder that our TA will be holding help hours tonight from 5 to 7 p.m. And remember, you can find the link to that. It's not this link, it's the one other Zoom link we use, and that's on our Canvas homepage. I think it's in blue. And then the Math and Stats Center is now open for one-on-one tutoring if you're interested in extra tutoring, and that's free to all students. You could probably meet with them once or twice a week. But I just got an update 15 minutes ago that this is no longer right. So the way you should sign up if you're interested in getting one-on-one tutoring, it would be online via something like Zoom, is to go to the Math and Stats Center website. And I know I put that link somewhere. I can probably just bring it up right now. So you can sign up online. So let me show you how you would get to that page. So the easiest way to do it is to go to the Wake Forest math homepage. So that would be just math.wfu.edu. And then at the top, there's a Math and Stats Center link. If you just click on that, it'll bring you to the Math and Stats Center homepage, and there's this link called Planner here. Okay, so you would click on that, and that lets you schedule an appointment with somebody if you're interested. Okay, so there are tutors available if you would like to do that through the department. Okay. So any questions about that stuff? Cool. Well, let's jump right in then. Okay, so today we're continuing with our talking about limits today. So section 2.3 is well, the book calls it like the limit laws. And yeah, that's kind of the heart of it. But let's briefly remind ourselves, right? Like we talked a little bit about this idea of a limit, right? That if I take the limit as x approaches some number of some function, tells me what the value of f of x should be in some sense, or what the ideal value or best value is at c. So this limit, it can be important to think about it as an operation. So So it's an operation. So it's like squaring something or taking the square root of something. It's that sort of operation. It's something you do to functions, right? So if I have the limit as x approaches c, then, you know, there are kind of various things I could put here. And I could put different functions in this yellow spot. And for each function I put in, I could potentially get a different answer out, right? So it's like I take a function and then I apply the limit to it, and it usually turns it into a number, right? A limit typically turns a function into a number, or sometimes the limit doesn't exist, right? If the two one-sideds don't match, or later I'll probably even show you another example where it's even worse, another way that limits cannot exist. Okay, so first thing is the limit you can think of as an operation where you take the limit and then you feed it a function and then it spits out some number L, right? Or maybe the limit doesn't exist and that's what you conclude. Okay, and so our goal for today is to look at this limit operation and ask, like, if I feed it more and more complicated functions, how do I actually figure out what that limit is? Okay, and the idea is going to be we're going to learn the limits of basic functions. Okay, and then we're going to learn how to combine them. And this last part, learning how to combine limits, and by combine, I mean like add two functions, divide them, multiply them, compose them. That's what will be called the limit laws. Okay, so these are all on the summary sheet. So it's easier, instead of me writing them out, just to show you what's on the summary sheet. So this first part here, 1 through 8 here, these are what I call the basic limits. So these are limits that you'll just sort of take for granted. So what does the first one say? So if I look at number 1, this is saying basically if I take the limit of any number, so if my function is just a constant number, like say I take the limit of 3, it's a horrible 3, as x approaches some number like say 5. Okay, so what do you guys think that should be? Any ideas?
3.
Yeah, so what helped you come to that conclusion?
The example of number 1.
Sure, I mean, it tells you here that it should be the same thing, right? But if we think about it sort of graphically, because this is what we're going to be talking about tomorrow, so I'll give you sort of a preview. The function 3 is just a constant line, right? At 3. And we sort of talked about how limits are, like if I approach the number 5 from either side, from both sides, then the outputs are still approaching this number 3, right? Still approaching 3. And so yeah, that's why it's 3. And if I look at the next one, it says if I take the limit of just the function x, as x goes to say -2, this says that whatever I'm taking the limit at will be exactly what comes out. So this will be -2. Okay. And if you think about that on a graph, right, y equals x is just a straight line. And if I take the limit at -2, and I approach -2 from either sides, then the outputs both approach whatever this output is, which is indeed -2, right? Okay, so you might sort of start seeing a commonality between all these, right? If you look at, say, number 3, it says if I take the limit as of x to the n at x equals c, I just end up with c to the n. Here I end up with c to the 1 over n. So what do you notice is like in common here? Does anybody see it? Like what's common between all these rules? Any ideas? Well, if you think about it, like if you look at all these functions and you just plug c into them, what do you get? If you plug c in for x, you get the right-hand sides, right? So that's all this is saying is for these functions, you know, constants x, x to any power, yeah, really x to any power, sine, cosine, log, well, I guess not to negative powers, log and exponentials, the limit operation just plugs in the value, right? So if I take c and I plug it in here, I end up with c to the 1 over n. And that's all that's saying is that when I take a limit and my graph is a nice unbroken line, right? If I approach along the unbroken line, the output's going to be whatever the function already is, right? Okay. And later we'll talk about this as sort of having the property of being continuous. Okay. Okay, so like in summary, what this table is saying is that for all these functions, taking the limit at a value is the same as plugging in that value. Okay, so these are functions which taking the limit is really easy. You don't have to think too hard about. Okay. Okay. Now, what are we going to do with them? Well, let's say we had another example. So say I wanted to know something like what this limit was. The limit as x approaches 4 of 3x squared plus 1. Well, you know, I could go through drawing the graph and I could analyze it and see like, well, as x approaches 4, what are the outputs approaching? And that's, you know, that's still a valid way. But a sort of more mechanical and in some ways simpler way is to instead use what are called the limit laws. Okay, so the second part here is the limit laws. And basically what all these say is if I take the limit and I apply it to the sum of two functions, well, really that's the same as if I take the limit of each one individually and then add them. Right, so, you know, it turns out that these are all true. And we're not going to go through really the proof of them because we didn't really talk about the actual precise definition of the limit to save time. But if I wanted to take, say, like the limit of just like this. The limit as x approaches 3 of x plus 5. Okay. Well, this would say I can sort of distribute the limit onto each piece. So this would be the same as this. But then we just learned before, right, how to do both of these limits, right? Both of these limits show up, right? This one is number 2, and the second one is number 1, right? And so these are both cases where these limits are just equal to plugging the value of 3 in for x. So this will just be 3. There is no x here, so it just remains 5, and we have this, and so this is just 8. So this gives us quick ways to compute limits, okay? And it turns out that it works also for multiplication. So it also distributes, you know, onto both for multiplication. Then for this one, maybe we should do an example of that one. This one says if you have like a limit of like 3x, that's the same as pulling the 3 out front, right? I can pull the 3 through the limit. And now I know how to do this. This will just be 3 times 2 is 6. Right, does that make sense? So this one says I can pull constants out. It also works for division. So if you're dividing two things, you can put the limit on the top and on the bottom. You can also pass limits under powers. So an example of number 4 would be like, if you had the limit of cosine of x to the 57th power as x approaches, say, 0, well, I could put the limit inside. Right. And you can also do that with fractional powers, and then we know the limit of, sorry, this should be still an x. And then we know the limit as x approaches 0 is the same as plugging in, so this would be cosine of 0 all to the 57th power, and cosine of 0 is 1, so this all just ends up being 1. Okay. And so you can also do that with fractional powers like square roots. Okay. Okay, so if we go back to our example here, you know, if we were going to use the limit laws to do this, what we would do is we would first break it up into across the addition. So we would distribute the limit to both parts across addition. And whenever you do this, like sort of a distributing idea, that the number you're taking the limit at always stays the same, right? And then you'd have a 1 here. Okay, and so what's the limit of the second part, this part here? What do you guys think? What's the limit of 1 as x approaches 4?
1.
1, good. And what, then there's this rule that lets us pull constants out. So yeah, kind of the way I remember it is anything that doesn't involve this variable, you can usually pull through the limit. Okay, so this I can turn into 3 times the limit as x goes to 4 of x squared. And now this is one of those basic limits. It's x to a positive power. And so this second is just the same as plugging 4 in, right? So what is it? 16 times 3, 48 plus 1 is 49 maybe. Okay. Now something you might notice here is like if you compare 3x squared plus 1 to here, basically all that happened is I plugged the 4 in, right? Okay, so tomorrow we'll talk about functions that have that property, right? We already know that the basics ones have that property, but there's a lot more. And one example of a class of things that if you take any limit at any value, it's always the same as plugging in is polynomials. So functions that have that property are going to be called continuous. And so we're going to learn tomorrow that polynomials are continuous because you can do the same sort of idea for any polynomial. Taking the limit is always the same as plugging in for polynomials. Okay, so questions so far? Okay, so just as a warning, you can't always just go and use the limit laws willy-nilly. There are occasionally times you have to be careful. And so let me show you one. So this will have two parts. Maybe let's do each one individually. Okay, so if I have this limit, well, this is another example where I can split it up into simpler limits. So I would first break it across addition, because that's the two big pieces. Okay. And then the second one we know how to do. This one, right, the limit of cosine is on that list. And so we can just plug the 5 in. This will be whatever the number of cosine of 5 is. It's not a nice number. But for the first one, we can break it up into the limit of the top over the limit of the bottom. Let's see, let's make this so it looks nicer. So you'd end up like this, and then we know both of these limits, right? So this would be 13 over 5, and that would be our answer. Okay, but now compare this with, if I ask something very similar, and I try to do the same thing here, it's almost the same thing, right? The only thing I've changed here is I've changed from taking the limit at 5 to the limit at 0. Is if you try to do this again, you'll end up with a division by 0, right? So there's some of these laws that you have to be a little careful about. So if you go back to here and you look at this division law, it says this one only works if the bottom limit is not 0, which makes sense, right? Because if we try to divide by 0, it really doesn't have a specific meaning. It usually means there's some sort of vertical asymptote going on, or occasionally there's some sort of cancellation going on. Okay, so it turns out that this limit does not exist. And if you really wanted to prove that, you would show that the limit from the left and the limit of the right are actually different. They're infinite, right? Because remember, one thing we said is that when we take a limit and we are taking the limit of the number, that when you plug it in, you get a number that's not 0, so like the 13, divided by 0, that means there's a vertical asymptote there, right? And so it turns out like the limit from the right here is positive and the limit from the left here is negative, and so they don't match. Okay. Okay, so there are a couple of these limit laws where things don't work. And basically the only ways that they don't work are if you have division by 0. Let's see what happened here. Oh, there it is. If you have division by 0, it's bad. And if you try to put a negative under a square root, that's bad. The other one that you might run into is if you try to put a negative into a natural log, that also ends up bad. So, plugging things in where the function isn't defined is typically a bad idea. Okay. Okay, so that's kind of the basic idea. The rest is just kind of tricks. So let's look at another example, and then we're going to try some together. So what if I was to do something like this? Okay. So whenever you wait, this is not correct. I want a minus here on the bottom. Okay. So if we look at this and you think through all the limit laws, right? The limit laws will basically say, you know, if I try to use them, it'll say I could basically put a limit on everything, right? I could put a limit on here, I could put a limit on here, a limit on here, a limit on here, and all that would end up is basically the same as plugging in. And if you try to plug in here, because what it turns out is the first thing you should always look at when you try to compute a limit is just what happens when you plug it in. So if I try to plug -2 in, what do I get? And if you get a number out, that's fine. That's usually just your answer. But if I do that here, I end up with 16 minus 16 over 4 minus 4. I end up with 0 over 0. Okay. So if you ever plug in and you end up with 0 over 0, this is what's called an indeterminate form. Indeterminate form. And basically what an indeterminate form means is it could be anything. It means it doesn't tell you that the limit doesn't exist. It tells you that the limit could exist and be just about any number, or it could not exist. It basically gives you no information. So it's indeterminate. It didn't determine the limit. Okay, so 0 over 0 could stand for just about anything. And so what do? So it didn't tell us what the limit is, so the limit could still exist. And the idea here is to do a little bit of algebraic manipulation. So we kind of did one like this the other day. But if you run into a 0 over 0 situation, your goal is usually to try to get the 0 out of the denominator, right? To somehow get rid of the division by 0. And usually you have to do some sort of cancellation to do that. So the key here is going to be to factor the numerator. So does anybody see how we could factor the numerator? So I'd like to have two factors. What should the first factor be?
On top, it would be x squared minus 4 and x squared plus 4.
Right. So remember, kind of the idea we're using is whenever you have two numbers and you see you have two things subtracted that are the squares of something else, you can always factor that as a plus b, a minus b, right? And so kind of what I see here is I see like x to the fourth is x squared squared, and I see 16 is 4 squared, right? So I end up with x squared minus 4 times x squared plus 4, right? This is the difference of squares formula. Okay. And this is good because we see that these two things match, right? The x squared minus 4s. But you have to be a little careful. Like I can't just go canceling things willy-nilly because it changes the function. But why can I cancel inside a limit? Any ideas? Well, the idea is, and it's probably good to remind you, is whenever you take a limit, the limit does not care whatsoever what the value of the function actually is at the value you're taking your limit is. So it could not be defined, it could be 12 billion, it could be 4. The limit doesn't care, it just asks, like, if I have a function and I know what's happening nearby, then if I approach from the left and the right, what should be there? Even if the function is defined like somewhere else, the limit will tell me what it should be, right? It'll tell me like what it thinks the real value should be, right? It would tell me this value. So that sort of makes sense. So that's why we can cancel inside the limit, is because outside the limit at -2, there's a division by 0, but when I'm taking the limit, all I care about are things that are not -2. So I can go ahead and cancel these. So canceling inside of a limit is fine. Okay. And so now this makes our lives a lot easier. Handwriting's getting sloppy. So if I cancel, I'm just left with x squared plus 4. Okay, and then we can go and use the limit laws. Or we could just skip directly, because we now know that polynomials will have this property, that the limit will be the same as plugging in. And what you'll end up with is -2 squared plus 4, which is 8. Okay. So that's one trick you might have to use, is if you end up with 0 over 0, then trying to do some algebra to cancel. So like whenever you run into 0 over 0, it usually means you have to do some extra work to either determine that the limit doesn't exist or do some algebra to figure out how to cancel something and then figure out what the limit is equal to. Okay. Okay. Okay, so now that you've seen some of this, I'm going to write some examples here. So please copy these down. And I'm going to put you into groups briefly to work through them. And then we'll come back to talk about the answers. Okay, so there's going to be 3 of them. And then number 3 looks a little more complicated. X approaches -2 of like that. Okay, so take a minute, write these down and start thinking about them. And in about a minute, I'll put you into some groups so you can talk them through for maybe 5 or 10 minutes, and then we'll come back and talk about them together. Okay, welcome back. So it looks like everybody got number 1 and number 2. Because you haven't seen anything quite like number 3, let me just kind of walk you through number 3. So like I was saying, when you first encounter a limit, your first instinct should just be what happens when I plug in, you know, C or whatever value you're taking the limit at. And if I do that here, what would happen? So I'd end up with, so -2 squared would be 4, plus 8, -8, -2. And we already kind of see that there's going to be an issue because the denominator is 0, right? Now, we should still compute the numerator, right? Because if the numerator is 0, it means I want to look for some sort of cancellation trick. But if it's not 0, then that tells me to look at infinite limits, where I kind of try to test to the left and the right of -2 to see whether it goes to plus infinity or minus infinity. And if we do that here, we see that we do get 0 over 0. So in that case, you want to be looking for a cancellation trick. So you want to do some algebra here to get something to cancel out of the denominator. Okay, and the trick here, guys probably will remember this once I show you, is what's called multiplying by the conjugate. So basically, if you have two numbers, either a plus b or a minus b, the conjugate of it is just the same thing but with a minus. So this is called the conjugate. Okay. So we're going to take the conjugate of the numerator. And the reason I'm doing that is because I know this trick comes out to be the difference of squares, right? And so the idea is it'll get rid of the square root, because the square root's kind of pesky. So the conjugate here would be the square root thing minus 8. Come on. And then we would have minus x. And we have, okay. And I can't just go multiplying by a limit by various numbers or equations, right? Because that would change what the limit is. So I can only multiply by 1, because multiplying something by 1 doesn't do anything to it. So I have to divide by whatever I multiply by, because this whole thing is just basically a fancy way of writing the number 1, right? So I'm multiplying by 1 in a fancy way. And let's see what happens here. Okay, so if I think in the numerator, this is like a plus b times a minus b, right? So the top will just come out to be a squared minus b squared. A squared is just the square root thing squared. So that gets rid of the square root. So in the numerator now, we'll just have x squared minus 4x minus 8 without the square root. And then b squared, well, b was x, so x squared is just x squared, right? So that was a squared minus b squared. And then on the bottom, well, nothing really pretty happens, so we just kind of write it down. Okay, so I end up with this mess, right? Which almost looks like I made it worse, but what we can notice here is I have an x and I have a minus x, right? So these two things cancel, right? X squared minus x squared is 0. And then, so let's write down the simplified version. So I just have minus 4x minus 8 times this mess minus x. Okay, is everybody with me? Cool. Now remember, our goal here was to get division by 0 out of the denominator. And the term that was causing the division by 0 was here. So I'd like somehow to get a term that matches that to appear in the numerator. Does anybody see a way to do that? How can I get an x plus 2 to appear in the numerator?
You factor out -4 in the top.
Great, thank you. Yeah, if I factor -4 out on top, then we're left with this. This big mess. And then, yeah, so now we've got it in a form where we have x plus 2 over x plus 2. So anything divided by itself is basically 1, except at -2. It's actually 0 over 0, but we don't care about at -2. So we can replace this with 1. And what we're left is, so we're basically canceling them. Okay, and now we're in good shape. Okay. It's going to be bigger. Okay, so if we cancel out, we end up with this little simpler thing. Okay. And whenever you've canceled something out of the denominator that makes you think that you got rid of the division by 0, what you should now try is you should just try go back to the beginning, plug in -2 and see what happens. And if it ends up being a number, then you're done. If it ends up being, a division by 0, it means you either have more work to do or you have to look at it as a vertical asymptote and look at the infinite limits. Okay, so, but if we just plug in here, we might think that it might be equal to, well, -4 is just the top. And then what did we end up here? We did this calculation already. What did the square root end up being? Just 2. So it ended up being the square root of 4 minus -2. So that would be -4 divided by 2 plus 2. That looks like me to be a -1. Okay, so the whole thing works out to be -1, but let's remember the main trick here was, we looked at it at the beginning. We said if I plugged in -2, I ended up with this indeterminate form. And because I saw this term on the numerator where it had a square root plus another term, it made me suspect that maybe this multiplying by the conjugate trick here would work. So this is another good one to have in your toolbox. And you have to remember, whenever you do that, you have to divide by that same conjugate to avoid actually changing the limit. Okay, so questions about this problem?
Will you scroll down a little bit? Sorry.
Sure. Is that good? Alrighty, so there was one limit law I haven't mentioned yet. And it had to do with inequalities, which I know you guys love. But let me show it to you on the summary sheet. It's the very last one. It's number 7 here. So we're talking about number 7. Okay, so what this one says, let's see if we can get it so we can read it. It says if you know you have two functions, f and g, and you know that g is always bigger, or at least as big, close to the place you're taking the limit, then same is true of the limits, right? So kind of what we're saying is if I start with knowing that g is at least as big as f, then I can put limits on both sides and the same thing is true. Okay, so I can go from an inequality between just functions near a value to knowing that their limits will have the same inequality. Okay, which makes sense. And I'll draw you some pictures in a minute. Okay, so the way I like to remember this is is that limits preserve inequalities. You know, it's kind of like if you take an inequality and you multiply it by a positive number, the inequality stays the same. So I would say, you know, multiplying by positive numbers also preserves inequality. You know, if you multiply by a negative number, it doesn't. Okay, so limits preserve inequalities. Okay, so why is this useful? Well, let's look at an example. Okay, so there's this really weird looking function. So I'm taking the sine of 1 over x and then I'm multiplying it by x squared. And I'm asking, well, what happens as x approaches 0? And, you know, and based on what we were talking about before, you might think, well, if I just try to plug in 0, you know, I would get 0 squared times sine of 1 over 0. And so you might suspect that maybe there's a vertical asymptote because of the 1 divided by 0, but because that's inside of a sine, you know, that no longer makes sense. Because I don't know, like, what sine of 1 over 0 is. So this is just a big, like, I don't know what this is. It's 0 times something that makes sense. Doesn't make sense. Okay, so we don't, like, that really didn't tell us much. It seems kind of meaningless to try to think about it this way. But this sine of 1 over x is a very curious function that maybe I just want to show you briefly. That if I forgot the x squared out front, and I just did sine of 1 over x, this is a very funky function. So let me show you a graph of it. So this is the graph of sine of 1 over x, just sine of 1 over x. So what's happening is it looks kind of like a sine. It goes up and down, but as it gets close to the origin, it starts going up and down faster and faster. So if you zoom in, let's see. It's being a little slow today. You can see if I zoom in that it sort of starts wiggling faster and faster until the calculator starts having a little bit of trouble with it, right? Okay. And you know, you can see I'm pretty far zoomed in, and like near the origin, it just looks like a blur. It's moving up and down that fast. And so like we're asking, well, what happens at 0? And it's very unclear. And what's happening is that the function bouncing up between -1 and 1 so much means it never settles towards any particular value. Because it always just keeps going up and down too fast to actually say, well, I think the limit is maybe 0. But if I go just a tiny bit further, then it's 1, and then it's -1, and then it's 0, and -1, and it keeps jumping up and down. And so in the end, what you realize is that this is an example of a limit that doesn't exist. And it's for this other weird reason, just that the function never settles down to a particular value near 0. It has this weird property that it goes up and down kind of infinitely fast near 0. Okay. But, so it doesn't exist. But if I add the x squared, let's see what happens. Okay, so that was sine of 1 over x. Let's see. Why won't it let me? There it goes. So if I multiply this by x squared, no, x squared, And let's maybe zoom back out. Nope, too far. Something didn't go right here. Doesn't like that. Maybe I have to write it first. Well, it's not going to agree with me, so let me just draw you a picture. It was working earlier. But what does sine of 1 over x times x squared look like? It looks roughly like this. So it looks pretty similar, like far away. So out here, it looks kind of like a sine, but then as it gets closer to the origin, it starts wiggling faster and faster. But it also gets smaller and smaller. And then it does the same thing kind of going the other way. It wiggles up and down, but then it starts getting a little bigger and bigger. And then it starts oscillating slower and slower. Okay, so this one doesn't have the same issue, right? Because if I look at the origin, all these things are getting very close to zero at zero. Okay, so it turns out that this limit is going to equal 0. Okay, because, you know, near 0, x squared gets 0, so it's kind of making it close to 0. But, you know, it's kind of hard to guess that just from all these graphs, because these graphs are kind of weird, right? Okay, so let me show you a kind of more mathematical way of thinking about this. So the key fact in all this, maybe that's not a good color to write in. Is that if I take sine of anything, what's the biggest output that can come out? We kind of talked about this earlier. What's the biggest output that can come out of a sine function? Anybody?
One.
Yeah, 1. And the smallest is -1. So no matter what you plug into a sine, the output is always going to come out to be between -1 and 1. Okay, so that means even if I plug in 1 over x, as long as x isn't actually 0, this will also hold. Okay, so this is a very useful thing to remember. That holds for cosine as well. Right? It doesn't hold for tangent or cotangent, but it holds for sine and cosine. So this is true whenever x is not 0. Okay. Okay, now if I take this inequality and I multiply it by x squared, now remember, x squared is a positive number if x isn't 0, right? It's either positive or 0 because of the squared. And so when I multiply an inequality by a positive number, they all stay the same direction, right? So this, if I multiply through by by x squared, I end up with minus x squared So this ends up being true, right? And what I'm trying to engineer here is I'm trying to engineer this to match the limit we were looking for, right? Okay, so is everybody with me on why that inequality is true? So that's true for all x's except for 0, because 0 doesn't make sense. Now, we just had this limit law that says if I have an inequality between functions, then it's also true in the limit. So if I just put limits on all the sides, this is also true, right? Because limits preserve inequalities. So then I'm going to put the limit at 0 in on all the sides. Sorry, let's do it. Let's put the minus in here. X squared sine of 1 over x. Okay, so that limit law tells us I can just put limits everywhere and it's still true. And the reason this is nice is because what's this limit equal to? Well, that's basically one of those basic limits with an extra minus. So this one's just 0, right? And this one on the other side, I can also just plug 0 into that. So that one's also just 0. And I'm left with this limit in the middle. Right? Remember, this was the original limit we were looking for. That's kind of how I engineered this whole thing. And right, remember, when you apply a limit to a function, it's just a number. So if you know a number's at most 0, and the smallest it could ever be is 0, what does it have to be? If a number's between 0 and 0, what's its only option left?
0.
0, yeah. Okay. So we can conclude from this that this limit is in fact 0. Okay. Okay, so this is an example of what's called the squeeze theorem. Okay. And why is it called the squeeze theorem? So if I go back up to this graph, so remember this was x squared times sine of 1 over x. And if you draw the two parabolas, so I usually draw these first, but if you draw x squared kind of follows the tips of these sine functions. So this, so I guess in reality this, whoops, that's way too much to erase. And on the bottom, it kind of does the upside down thing. Whoops, let's do that in blue. Kind of follows these here. So that's minus x squared. So we have x squared and we have minus x squared. And the x squared sine of x is kind of squeezed in the middle, right? This gets squeezed to 0. Right, so this is what that inequality was saying, is that this x squared sine of 1 over x is always below x squared and always above minus x squared, right? And as you go to 0, if you come in here from either side, the x squared and minus x squared both go to 0. And so the thing that's between them must also get 0, right? It's kind of being squeezed here. Okay. Until there's only one possible thing it could be, and that's what both of these are at 0. Okay. Okay, so this is what's called the squeeze theorem. Let me show you the formal statement. It's also on this summary sheet, so you don't have to copy it down. Okay, so here's the formal statement of the squeeze theorem. And the basic idea is, it's saying if you have three functions, so say you have a function f, and then you have a function g, which may be, no, that can't be g. Let's do something. So maybe that's g. So f is the, oh, I've done this backwards. Wait. Let's say this is g. So f is the smallest one. Then bigger than that is g. And then h has to be the biggest one. We can do that one in red as well. So say you have another h1. Does maybe something like that. And so it's a picture similar to what we did before, except it doesn't have to be at 0. Okay, so if you have three functions where, h is the biggest, g is the next biggest, and f is the smallest, close to some number here, right? And you know that as you approach c, the top and bottom ones, right, they all approach the same thing. They're all approaching whatever this point is, whatever this number is. Then the green one, which is between them, also has to be equal to that, right? So the limit of the g one has to be equal to the limits of the other two, because it's between them. Okay, so that's like what we did before, right? We found that the limit of the big one was 0 and the limit of the small one was 0. So the one in the middle also had to be 0. Okay, so that's the idea, is you squeeze it between the same number and it has to be, then the middle one has to also be equal to the same number. Okay, so questions about that? I'm not going to ask you to do too many of these. I think there's one on the worksheet that you can follow kind of the same formula as what we just did in class. There's an example down here. That should be very similar to what we did. Okay, so I think we're about out of time. I think we got through just about everything. Just a reminder that there is the help session from, what did I say, 5 to 7, I think. And I can stick around for a few minutes if there's questions too. Yeah, 5 to 7 tonight. And the link is on the Canvas homepage. Okay. All right, great. Have a great day, guys.
Thank you. Thank you.
Thank you.
Thank you.